Hello, everyone. We are the University of Wind Aeronautics team, otherwise known as WinSAT. I'm Madeline McQueen, and my colleague Attila and I will be presenting on behalf of WinSAT's Mechanical Capstone team. So here's a little overview of what we'll be talking about today. I'm just going to jump right into it. So the Canadian Satellite Design Challenge 2018 to 2020 is the competition that WinSAT is competing in. It is a Canadian-wide competition for teams of university students, undergraduate and graduate, to design, build, test, and potentially launch a small satellite. This satellite will be a 3-unit or 3U cubic nanosatellite with an Earth observation payload of an optical imaging camera. Its dimensions are to be 34.05 by 10 by 10 centimeters. It will be built through the coordination of 8 divisions: attitude determination and control systems, business, command and data handling, electric power systems, payload, radio frequency, structural, and thermal. This presentation will highlight the accomplishments and deliverables of the Mechanical Capstone team. In October, the team presented at the CSD Critical Design Review, where we were awarded first place. Shown here is some of the publicity that the team received after this win. This is the most up-to-date model of the satellite. Here it is shown with and without solar panels so that the internal components can be seen. Some of the most design-intensive components will be discussed throughout this presentation. The antenna deployment system is required to deploy the satellite's dipole antennas once it has been ejected from the launch vehicle. These antennas will allow the satellite to communicate with the ground station at Windsor through the selected 144 MHz and 437 MHz amateur radio frequencies. The antennas are released using a burn wire attached to a resistor and the release door. As the wire is burned, the door is opened and the antennas are released, a method that has proven space heritage. During the launch, all electrical systems on the satellite need to be inactive in order to avoid interference with the launch vehicle. This is accomplished through the use of a spring plunger and a microswitch. Once the satellite is released from the vehicle, the microswitch lever is released and the satellite's electrical systems turn on. Similarly, the separation spring stays in the depressed state when the satellite is inside the launch vehicle. Once the satellite is ready to be launched, the vehicle door opens and the spring force in the plunger ejects the satellite out.
One subsystem of the satellite is the attitude determination and control systems, which are responsible for determining the satellite's orientation and position in orbit, as well as actuating the body to the desired orientation. One way of doing this actuation is with reaction wheels, which offer high torque actuation, allowing for fast and accurate attitude control. There will be 4 reaction wheels in a pyramidal design in order to meet dimensional constraints and redundancy requirements, as well as to provide torque in all 3 axes. The maximum wheel size was found to be 38 mm in diameter and 10 mm in height, which gives the required torque in the available PC-104 board space. This overcomes the disturbance torque, momentum storage, and slew torque requirements. Magnetorquers are another method of ADCS actuation using electromagnets that consist of a long coil of magnetic copper wire looped around an iron ferrite core. This provides coarse 3-axis control of the satellite's attitude using the magnetic dipole moment induced by the wire and the Earth's magnetic field. Magnetorquers are used for detumbling the satellite following initial ejection from the launch vehicle, as well as desaturation of the reaction wheels. The magnetorquer's core size was determined by the ADCS electrical team, and the structure was designed accordingly. Due to the harsh thermal environments of low Earth orbit, thermal simulations are conducted on the satellite model using Siemens NX. In order to reduce the computational time, the structural CAD model has been simplified and recreated in NX. Sun-synchronous and International Space Station orbits are both considered in simulations in compliance with the CSDC supported mission profiles. Many considerations are taken into account when creating the thermal simulation, including solar radiation fluxes, Earth's albedo, Earth's infrared radiation emissions, and thermal heat generation. All heating loads have been modeled using finite element features to account for radiation, conduction, and internal heat loads from PCB components. The NX Space Systems Thermal Solver is used to gather temperature data throughout the orbit in direct solar and eclipse regions. The results of these simulations are focused on the hot and cold cases for the satellite to gather maximum and minimum temperatures experienced for each component. Listed here is the project budget for WinSat. The budget is dispersed amongst the entire project, as some subsystem components are disproportionately more expensive than others. More specifically, our team has chosen to go with components that have space heritage and certification for the electrical power systems, namely the EPS module and battery, command and data handling module, and the radio communications transceiver. The other component costs are associated with in-house development, commercial components off the shelf, and any associated manufacturing costs. The CSGC timeline is provided for reference for our development relative to the competition. We are currently in engineering design phase 3, which involves finalizing various designs and simulation results, submitting and receiving components, and in-lab assembly, integration, and testing. The environmental testing was originally slotted for the end of June at the Canadian Space Agency's David Florida Laboratory in Ottawa. Here we can see the WinSAT Gantt chart, modified to only show the general ADCS, thermal, and structural development goals and timelines, omitting the other subsystems and divisions. Most of the development time has been allotted to assembly, integration, and test, as that is the most unpredictable aspect of spacecraft engineering. Along with various academic, logistical, and general development timeline issues that may arise, it is necessary to allocate more time than normally expected for these steps leading up to the competition. The timeline for after the competition has also been omitted as it is also allocated for further development required pending the environmental testing results from the competition. Throughout the final semester, WinSat will continue meeting development goals for spacecraft simulations, CAD models, PCB designs, software architectures, and more, as partially outlined in the table shown here. In-house integration and testing will be completed if WinSat members are allowed back on campus. And that concludes my presentation. Thank you for your time and consideration.